In this section, we introduce the main elements of logic and illustrate those elements using sentences written in English. First of all, there are linguistic issues of syntax and semantics. What are the syntactically acceptable expressions of our logical language, and how do we know that our sentences say what we think they say? Second, there's the concept of logical entailment. Given a set of sentences that we know to be true, which other sentences must also be true, according to our semantics? Finally, there is logical reasoning. Are there symbolic manipulation procedures that we can use to derive these necessary conclusions via purely syntactic manipulation of the initial sentences? As we shall see, these three issues are closely related to each other. Consider the interpersonal relations of a small sorority. There are just 4 members: Abby, Bess, Cody, and Dana. Some of the girls like each other, but some do not. Here's one set of possibilities. Abby likes Cody, Bess likes Cody, and so forth. Let's assume that we do not know this information ourselves, but we have informants who know the girls and are willing to share what they know. Each informant knows a little about the likes and dislikes of the girls, but no one knows everything. Here's where logic comes in. By writing logical sentences, each informant can express exactly what he or she knows. No more, no less. For our part, we can combine these sentences into a logical theory, and we can use this theory to draw logical conclusions, including some that may not be known to any one of the informants. Here we see one such collection of sentences. The first sentence is straightforward. It tells us that Dana likes Cody. The second and third sentences tell us what is not true without saying what is true. The fourth sentence says that one condition holds or another, but does not say which. The fifth sentence gives us a general fact about the girls Abby likes. The sixth sentence expresses a general fact about Cody's likes. The last sentence says something about everyone. As we go through these videos, we will occasionally come upon interactive exercises like this one. Different exercises have different purposes. In some cases, they are simple demonstrations. In other cases, they test one's understanding of the ideas just presented. And in yet other cases, they motivate upcoming material. This exercise tests one's intuitive understanding of logic by creating various states of Sorority World that satisfy the sentences like the ones we've just been seeing. Do the exercise, and when you're done, continue with the video. Sentences like the ones we have just seen constrain the possible ways the world can be. Each sentence divides the set of possible worlds into 2 subsets, those in which the sentence is true and those in which the sentence is false. Believing a sentence is tantamount to believing that the world is in the first set. Given 2 sentences, we know that the world must be in the intersection of the sets of worlds in which the first sentence is true and a set of worlds in which the second sentence is true. Ideally, when we have enough sentences, we know exactly how things stand. Unfortunately, this is not always the case. Sometimes a collection of sentences only partially constrains the world. For example, there are 4 different worlds that are consistent with our Sorority World sentences. Even though the set of sentences does not determine a unique world, it's often the case that some sentences are true in every world that satisfies the given sentences. A sentence of this sort is said to be a logical conclusion from the given sentences. Or said the other way around, a set of premises logically entails a conclusion if and only if every world that satisfies the premises also satisfies the conclusion. What can we conclude from our set of sentences? Quite a bit, as it turns out. For example, it must be the case that Bess likes Cody. Also, Bess does not like Dana. There are also some general conclusions that must be true. For example, in this world with just 4 girls, we can conclude that everybody likes somebody. Also, that everybody is liked by somebody. One way of making this determination is by checking all possible worlds. For example, in our case, we notice that in every world that satisfies our sentences, Bess likes Cody. So the statement that Bess likes Cody is a logical conclusion from our set of sentences. Unfortunately, determining logical entailment by checking all possible worlds is impractical in general. There are usually many, many possible worlds, and in some cases there can be even infinitely many. The alternative is logical reasoning, namely the application of reasoning rules to derive logical conclusions and produce logical proofs. As an example, consider a proof that starts with the premises shown above and shows that Bess likes Cody. We know that Abby likes everyone that Bess likes, and we know that Abby does not like Dana. Therefore, Bess must not like Dana either. If Bess did like Dana, then Abby would like her as well. At the same time, we know that Bess likes Cody or Dana. Consequently, since Bess does not like Dana, she must like Cody. The concept of a proof, in order to be meaningful, requires that we be able to recognize certain reasoning steps as immediately obvious. In other words, we need to be familiar with the reasoning atoms out of which complex proof molecules are built. One of Aristotle's great contributions to philosophy was his recognition that what makes a step of a proof immediately obvious is its form rather than its content. It does not matter whether we are talking about blocks or stocks or sorority girls. What matters is the structure of the facts with which we are working. Such patterns are called rules of inference. As an example, consider the rule of inference shown here. If we know that all Accords are Hondas, and we know that all Hondas are Japanese cars, then we can conclude that all Accords are Japanese cars. Now consider another example. If we know that all Borogovs are Slithy Toves, and we know that all Slithy Toves are Mimsy, then we can conclude that all Borogovs are Mimsy. What's more, in order to reach this conclusion, we do not need to know anything about Borogovs or Slithy Toves or what it means to be Mimsy. What's interesting about these examples is that they share the same reasoning structure, namely the pattern shown here. The existence of such reasoning patterns is fundamental in logic, but raises important questions. Which patterns are correct? Are there many such patterns or just a few? How many do we need? Let us consider the first of these questions first. Obviously, there are patterns that are just plain wrong, in the sense that they can lead to incorrect conclusions. Consider, as an example, the faulty reasoning pattern shown here. All x are y, some y are z, therefore some x are z. Now let's take a look at an instance of this pattern. If we replace x by Toyotas, and y by Japanese, and z by made in America, we get the following line of argument, leading to a conclusion that happens to be correct. All Toyotas are Japanese, some Japanese are made in America, therefore some Toyotas are made in America. On the other hand, if we replace x by Toyotas, and y by cars, and z by Porsches, we get a line of argument leading to a conclusion that happens not to be correct. All Toyotas are cars, some cars are Porsches, therefore some Toyotas are Porsches. Not so good. What distinguishes a correct pattern from one that is incorrect is that it must always lead to correct conclusions. That is, conclusions that are logically entailed by the premises. As we will see, this is the defining criterion for what we call deduction. Of all the types of reasoning, deductive reasoning is the only one that guarantees its conclusions in all cases. It has some very special properties and holds a unique place in logic.